In this video, we will learn about mutually induced EMF. So what will we do is, first we will consider two coils A and B which are placed close to each other. Let me draw two coils and I will call these coils as coil A and coil B. I will name it as one coil as coil A, the other one as coil B. We have two coils placed close to each other. Now next, what will we do is, we will connect this coil A to a battery through a switch. So by inserting a switch, we have the control over circuit. We can make on and off whenever it is required. According to our wish, we can switch on or we can switch off. So that is the purpose of switch here, because we can on and off according to our wish. Now what will we do with coil B? Now to coil B, we will connect a galvanometer to check whether there is any current in the circuit, because if there is a current in the circuit, the galvanometer will show the deflection. So this is the arrangement which we can use to know about mutually induced EMF, or how an EMF gets induced due to mutual induction. Now coil A and B are placed close to each other in such a way that if there is any flux produced in coil A, which also links with coil B. That is why I am placing coil B very close to coil A. Why? Because coil A is connected to a battery and hence a current can flow through coil A. But coil B I am not connecting to any battery or any supply. I have just connected it to a galvanometer. Now when the switch is off, in this case, now the switch is off. So there is no current in coil and no flux, and hence there is no induced EMF. So the circuit is idle. No current, no flux, no induced EMF. So now let us see what happens when you close the switch. No current means the galvanometer will also show no deflection. So you can write that, switch off. When the switch is off, no current in coil A, no current flows through coil A, no flux, no induced EMF, no current in coil B also, no current in coil B also, and no galvanometer deflection, or galvanometer zero deflection. No deflection in the galvanometer, or galvanometer shows no deflection. No deflection, I will just write G because it is understood. Okay. Now next case, what will we do is, we will close the switch. This is a switch off condition. No current, no flux, no induced EMF, no deflection in the galvanometer. Now we will see what happens when you close the switch. Switch on. So S is on. A current starts flowing in coil A, right? Switch on. So we will close the switch. Okay, the switch is closed. Now a current starts building up in coil A. Switch S is closed or switch is on. Current in coil A start rising from 0. Current in coil A starts increasing from 0 to a certain fixed value. to a certain finite value. We don't know, maybe we can say it is capital I. Say I. Okay. Some finite value. You know, current through the inductor will not increase suddenly, just in case of resistor. It slowly builds up. That means when current increases from 0 to I, the flux which is produced in this coil A also will increase from 0. So the flux changes with respect to time. When the flux linking coil A changes, there gets an EMF induced in coil A, and which is known as self-induced EMF. So flux also increases from 0. Okay, flux start increasing from 0, increases from 0 to a finite value. Now, as coil B is placed very close to coil A, what happens? The flux which is produced coil A also links coil B. The flux which is produced in coil A also links coil B. Therefore, the flux linking coil B also increases from 0. Why? Because coil B is placed very close to coil A, and hence the flux which is produced in coil A also links coil B, and the flux in coil B also increases from 0 to a finite value. That means the flux is actually varying with respect to time, and due to this there gets an EMF induced in the coil B or in coil B, and this induced EMF is known as mutually induced EMF. So next I can write the flux produced in coil A also links coil B. This flux increases from 0 to a finite value as the flux varies with respect to time, or flux is varying. There gets an EMF induced in coil B. Flux produced in coil A also links coil B. This flux increases from 0 to a finite value, and hence, or you can write, this change in flux with respect to time, this rate of change of flux, or due to this rate of change of flux, or due to this, an EMF is induced in coil B, and this is known as mutually induced EMF. Now, what is mutually induced EMF? The EMF induced in one coil due to change in current in the other coil. So this due to this EMF, how do we came to know that there gets an EMF induced in coil B? The galvanometer shows deflection. So the induced EMF is indicated by the galvanometer. The galvanometer will show some deflection. Now after some time, once the current reaches its finite value I, there won't be any increase in current, and the flux linking coil A will not be changing with respect to time, and hence the flux linking in the coil B will also not be changing, and the EMF induced becomes 0, and the galvanometer comes back to 0 position, or the deflection shows 0. So this also indicates that the EMF gets induced only when there is a change in flux. Now again you can repeat this, like what you can do now is open the switch. Now when you open the switch, what happens? The current is now at I. Once you open the switch, the current reduces from I to 0. When the current reduces, again the flux will also decrease, and the EMF gets induced in the coil, both the coils, coil A and B. The EMF induced in coil A is known as self-induced EMF. The EMF induced in coil B is known as mutually induced EMF. Now in this case, if you observe the galvanometer, the deflection will be onto the other side. Why? This is because the current is reducing, that means the flux is also reducing. So the EMF induced is in the opposite direction when compared to the previous case. The EMF induced always opposes the very cause producing it, that is the Lenz's law. So now you can say that the EMF induced in coil B is mutually induced EMF, and EMF induced in coil A is self-induced EMF. So we can conclude by saying that whenever the current in coil A changes, the flux linking with coil B also changes, and an EMF known as mutually induced EMF is induced in coil B. Whenever the current in coil A changes, the flux linking with coil B changes, and an EMF known as mutually induced EMF is induced in coil B. Now the important points to be noted, I'll just write next. So whenever the current in coil A changes, the flux linking the coil B changes, and an EMF known as mutually induced EMF is induced in coil B. Now points to be noted. First point, the mutually induced EMF in coil B persists as long as the current in coil A is changing. The mutually induced EMF in coil B persists or exists as long as the current in coil A is changing. If current becomes constant, in coil A, then the flux will not be changing, and hence there is no EMF induced. Now, so how much EMF is induced? The magnitude of this induced EMF will depend on the number of turns in coil B and also the amount of changing flux linked with it, because it is N phi by I, right? So Later on I'll give you the equation also for induced EMF, how we can calculate. First we'll write this: the magnitude of mutually induced EMF depends upon the number of turns in coil B. And the amount of changing flux linked with it, and the amount of changing flux linked with it. And the third one, the direction of mutually induced EMF is such that it opposes the very cause producing it, that is Lenz's law. The direction of mutually induced EMF is such that it opposes the very cause producing it. That is actually Lenz's law. In bracket you can write it as Lenz's law. So these are three important points to be noted with respect to the mutually induced EMF.